Hello, welcome to today's video. What we're going to do first is go over the homework due today. So please locate that. That was this worksheet here. And what I'm going to ask you to do is I'm going to put questions in the Edpuzzle. I'd like you to share your answers with me for 2 and then 3 and then 8 and then 10 and then 13. There'll all be different questions in the Edpuzzle. If you need a radical, one way we do that is we type SQRT for square root. So like square root of 7 won't be in your answer, but if you wanted to type that, you could type it like this. And you won't be able to type pi if you need it, so pi. All right, thank you for sharing your answers. And now I'll share all the answers with you and you can check those. So let me zoom in a little bit. Taking a look, we have some factoring review first. And as you know, your factors can be in either order, but the signs matter. So make sure you have the minus with the 6 and the plus with the 3. And then you guys did some evaluating and then some solving for theta. The program that I used to make the worksheet, when they put their answers for theta, they put it in curly braces. They're just, you don't need those. You can just have the 2 answers. And of course, the answers could be in either order. I did all my answers in radians because that's what the directions said. So for this, if you put 135 degrees and 315 degrees, those are also correct, but you didn't follow the directions. So just be careful with that in the future. All right. And this was practice for our weekly graded do nows, which will resume this week. Moving on to today's lesson. Let's go ahead and do a warm-up problem before we really get started. And for that warm-up problem, please find a spot in your notebooks and go ahead and simplify 3 minus 5i, that quantity being squared. Now, just as a hint before you start, when you go to square a quantity, that means you multiply it times itself. So don't just square the 3 and square the 5i. You actually have to FOIL that out and simplify, please. All right, and hopefully for your answer, you got negative 16 minus 30i. Most common mistake on this is rushing the part with the 25i squared. When you do last times last, that's negative times a negative is a positive, 5 times 5 is 25, and I times I is I squared. Because I squared is -1, we will end up changing the sign. But a lot of people make mistakes right here, either putting a 5 instead of the 25 or ending up with the wrong sign there. So just be careful. All right, moving into today's lesson. For today's lesson, there is a worksheet. It would be a little more interesting for you if you don't look at the worksheet just yet. I'll tell you when to move over to the worksheet. But we're going to continue our work in section 2.4 with powers of I. And when it comes to powers of I, we're going to be looking at things like I to the first, I to the second, I to the fourth, and so on, I to the third. And I to the first, we know that's just the imaginary unit. That's the square root of -1. But we always replace that with I, so there's really nothing to do there. We know I squared is -1, because if you square this, you get -1. And now we want to simplify I to the third. So I to the third, we know that could be I times I times I, or another way to break that down is I squared times I to the first, right? Because if you're going to multiply those back together, you would keep the base and add the exponents. So there are different ways to break this down. This one looks pretty nice because we know I squared is -1. And then I to the first is just I. So that simplifies to negative I. So I cubed simplifies to -I. Now for I to the fourth, again, there's lots of ways to break this down. We know this is I times I times I times I. You could also do it as I to the, I'm going to do I to the second times I to the second, if that's all right. Okay, so I to the second times I to the second, we know that makes I to the fourth. And the reason I like this one is because that would be -1 times -1, because each I squared is -1. That gives us +1. We absolutely could have broken down I to the fourth as I to the third times I. I to the third, if you look back, is -I. So you'd have -I times regular I, which would be opposite of I squared. And I squared being -1 is going to bring us back to 1 anyway. Okay, so just as an alternate, you could do it that way. So let's continue on our way. For I to the fifth, there's lots of ways to break this down. Now, I have a favorite power of I, that's I to the fourth, because that comes out to just regular plain old 1. So it's not imaginary and it's positive. That's like the nicest one that I've seen so far. So when I go to break down I to the fifth, instead of doing like I to the second times I to the third, or I to the second times I to the second times I to the first, all of these would be I to the fifth. My favorite way to break that down is to use an I to the fourth, because that's my favorite power of I. So if I break this down to I to the fourth times I, I can replace I to the fourth with 1, and I end up with I. Continuing on our way, we know there's lots of ways to break this down. I'm going to do I to the fourth times I squared. I to the fourth is 1, because that's my favorite power of I. That's the one I'm going to memorize there. And then I to the second we already know is negative 1. For I to the seventh, we could break this down lots of different ways. I'm going to do it this way, because I to the fourth is 1. And if we look back for I to the third, I can replace that with negative I. And you might start to see something happening here, because when we go to I to the eighth, that's going to be 1 times 1, which is 1. And if you notice, the answers here, they are repeating. This is cyclic in nature. So if you look, what happens is your answers for your powers of I go I, negative 1, negative I, 1, and then they repeat. So then it goes I, negative 1, negative I, 1 again. So without doing any work, can you predict what I to the ninth, what you think that would come out to? That comes out to I. And you can get there lots of ways. Like, so if you wanted to, you could do I to the fourth times I to the fourth times I. So it'd be 1 times 1 times I. But I'm going to stop showing the work here, because this has that cyclic or periodic nature. So this is where you want to go grab the worksheet, because I have all of this already worked out for you. And I didn't put this stuff on the side, but I have all of this worked out already for you. You might want to put a star next to I to the fourth. And you might want to put a line here in between I to the fourth and I to the fifth, and between I to the eighth and I to the ninth, just to show where it starts to repeat. And the word I used is cyclic or periodic. When something repeats, we call it cyclic or periodic. So if we continue the pattern, I to the 10th, that should come out to negative 1. And I to the 11th should come out to negative I. And they do. You could check all these. And then I to the 12th is 1. And then that pattern continues from there. So what this leads us to is we actually can kind of develop a shortcut for how to evaluate powers of I. So if we wanted to find out what like I to the 37th was, or I to the 50th, we can develop a shortcut. And here's how that shortcut will work. Let me get a piece of paper here. Okay. So the way the shortcut will work, there's lots of ways to do this. Here's my favorite way. So I to any multiple of 4 is going to be 1. This is not proper mathematical notation, but this is a really nice way to kind of put this in your notes. If you have I to any multiple of 4, you're going to get 1. And we can justify that pretty easily. I'll do that in a moment. But if we know that I to any multiple of 4 equals 1, and then we know that I to the second is negative 1 and I to the third is negative I, then we can pretty quickly find any power of I we want. So please make a note that I to any multiple of 4 is 1. And then we've already established these two facts, but you kind of want to memorize those. And just to take a moment, you don't need to write this part, but just to justify that I to any multiple of 4 is going to be 1. As an example, here's like I to the 20th. 20 is a multiple of 4. So this is going to definitely come out to 1, because we can rewrite this as I to the 4th to the 5th, right? Because when you have a power to a power, you would multiply those together. So I to the 4th is 1, and 1 to the 5th is 1. So I to any multiple of 4. Let's go big here. Let's go 84. That's a multiple of 4, right? Because I can write that as I to the 4th to another power. So that's I to the 4th to the 21st. Because if you have a power to a power, you multiply those powers. So this is 1 to the 21st, which is 1. So with those two examples, it's certainly not a proof, but I think you're probably buying into this. I to any multiple of 4 equals 1. So if you memorize that and the fact that I squared is negative 1 and I cubed is negative I, you'll be able to evaluate any power of I you want. On the bottom of the handout, you have some space for some examples. So let's go ahead and take a look at a couple of those. I'll just leave this here because that's all we really need to know. So for some examples, let's go ahead and simplify. Please write down the directions. The directions will be simplified. I to the 37th. Okay. So if we know that I to any multiple of 4 is going to be 1, here's how I like to do this. And again, there's a lot of different ways you can do this. Here's my favorite way. What we're going to do is we're going to find a multiple of 4 that's really close to 37, but always go smaller. Okay. So a multiple of 4 that's close to 37 is 36. So I can rewrite I to the 37th as I to the 36th times I to the first. I to any multiple of 4 is 1, and I to the first is just going to be I. And that's it. So instead of having to continue out this pattern, we don't need to keep this pattern going all the way to I to the 37th to figure this out. We have a shortcut. And again, there's lots of different shortcuts that would work. This is my favorite. So if we find a multiple of 4 that's pretty close to this number, make sure it's smaller. You can then rewrite this, and you'll be able to simplify very quickly. So for example, 2, let's say you want I to the 50th. You don't have to write out all the powers of I up to 50. You just have to find a multiple of 4 that's pretty close to 50. So 50 is not a multiple of 4 because it doesn't divide evenly. 49, of course, is not because it's odd. But 48 is divisible by 4. So I'm going to rewrite I to the 50th as I to the 48th, and then I times I to the second, because if I times those together, I'd be adding the exponents. So this shortcut is going to allow us to replace this with 1, because I to any multiple of 4 is 1. And then I squared, we know from our previous lesson, is -1. And that's our answer. So this is a nice shortcut for any larger power of I. Let's try one more. I'm going to make it a little more complicated. Let's say that for our next one here, I have I to the 48th minus 2 times I to the 23rd plus 7 times I to the 102nd. Okay, it's a little crazy. I don't know why you'd ever want to evaluate that or simplify it, but we can. All right, so you're going to have to do each one of these. So I to the 48th, well, 48 is a multiple of 4. So guys, we can replace that immediately with the number 1, which is great. And then for I to the 23rd, you can work that out right here, or you can go off to the side. Go ahead and find out what I to the 23rd is. Hopefully you got -I, because you can rewrite I to the 23rd as I to the 20th times I to the 3rd. Again, we're looking for a multiple of 4 that's close to this number to start, because I to any multiple of 4 can be replaced with 1. And then I cubed, this one's a little new, so you might have to look back at the notes, but I cubed can always be replaced with -I. Okay, I'll clean that up in a moment. And then I have 7. And then for I to the 102nd, again, you can work that out right here, or you can go off to the side. Please go ahead and evaluate, find out what I to the 102nd is. Hopefully you got -1, because 100 is a multiple of 4, and I squared is -1. And if we just simplify, now I have 1 plus 2i minus 7. It's going to be -6 plus 2i. And I didn't put in the direction standard form, but let's go for standard form. So if you wrote 2i minus 6, can you go ahead and rearrange that? 2i minus 6 is not wrong, but it's not standard form. So let's go ahead and put that in standard form. All right, and you'll get some more practice with that tonight. But even if you had a little trouble following, if you didn't like the part where I was doing, expanding it and really showing the work, if you memorize these facts right here, and you can find a multiple of 4 that's close to your original exponent, then you can always just use that shortcut. And that's the way I'd recommend solving these. All right, we have 2 more things to cover in today's lesson. The next is on the back of the handout, which is going to be plotting complex numbers on the complex plane. So this is a complex plane. And it looks the same as our regular x-axis and y-axis, which is called the Cartesian plane. The Cartesian plane. But on the Cartesian plane, there's no room for imaginary numbers. So there's no room for imaginary numbers on the Cartesian plane. So that's why, even though it looks the same, we're going to call it the complex plane instead. And what we have on the complex plane is we have our real axis and the imaginary axis. The real axis is horizontal, the imaginary axis is vertical. And if we want to plot our first number here, and again, I just called them z sub 1, z sub 2, z sub 3 to give them labels. All right, I could have just as easily called this number A, like this one B, and this one C, just as labels like in the last video. But using subscripts is a good way to do this here. So if you want to plot 3 plus 2i, what you do is for the real part, you start at the origin. And for the real part, if the real number is positive, you're going to go to the right. If the real number is negative, you go to the left. So you're going to go 3 units to the right. And then the imaginary part is 2i. So what we're going to do is go up 2 units on the imaginary axis. And that's the location of the point z sub 1. It's very much the same as plotting numbers on the x and y axes. You use this component here to decide your left-right movement, and the coefficient of I gives you your up or down movement. And that's the location of z sub 1. Now for z sub 2, we have -4 plus I. So we start at the origin. For the real number, we're going to go 4 units to the left on the real axis. And then the coefficient of I is 1. So this says go left 4 and then up 1. And that's the location of z sub 2. And my last one here is z sub 3. I have 6i. We know that can be written, that pure imaginary number can be written as 0 plus 6i. So we're not going to go at all left or right on the real axis from the origin. We're going to stay right where we are and just go up 6 units. 3, 4, 5, 6. And that's the location for z sub 3. Okay. And I think you're probably okay plotting complex numbers on the complex plane. That's about all there is to it. So the last part of today's lesson is the absolute value of complex numbers. The absolute value of a complex number is the complex number's distance from the origin when you plot on the complex plane. Now, in order to find it, there's a couple ways. I'm going to introduce a formula here for you. And that formula is, if you want the absolute value of a complex number in the form a plus bi, you do the square root of a squared plus b squared. So you do the square root of the real number plus the square root of the coefficient of I. Notice there's no I in here. So when you go to do the square root of a squared plus b squared, you don't put an I in there at all. Okay. And I'll show you what this formula is, because it's really just the same thing as the Pythagorean theorem. But if you would like to memorize it as something new, you can. So let's go ahead and use the examples from above. So for our first example, I'm going to do the absolute value of z sub 1. So that's the absolute value of 3 plus 2i. And if we just plug into our formula, our a is 3 and our b is 2. You don't put an I in here, just the coefficient of I. And what we get from that is the square root of 13. And that's all there is to it for finding the absolute value of a complex number. But to try to give you an idea of what that really means, if we look back here, you don't need to draw on this, but I'm going to draw on it. We just found the distance from the origin to this location. So this formula that you're using down here, it's really just a new take on the Pythagorean theorem, because we found this distance right here. So if we want to make a triangle, we can drop an altitude. I'll go to the x-axis because you guys know that's my favorite axis. This distance is 3, this distance is 2, and this is the distance we're trying to find. Let me call it r, just because. I could call it h for hypotenuse. And we don't need a brand new formula for that. We already know how to do this. If we want to find the hypotenuse there, we would do 2 squared plus 3 squared equals r squared. And then to find r, we would take the square root of that value. So this is really not a brand new formula. This is the same as the Pythagorean theorem. So you can think of it either way, whichever way you prefer. All right, now for z sub 2, so we're going to find the absolute value of this number next. So we want to find that distance. So if you wanted to, you could just drop an altitude right there, make a triangle, and use the Pythagorean theorem, no problem. If you'd prefer to just kind of have this as a new formula, that's fine as well. So what's going to happen here is we're going to do the square root of the real number squared, and then the coefficient of I is 1. And what we're going to end up with here is the square root of 17. And that's the distance from the origin to the point z sub 2. And for the last one, z sub 3, the formula does work here for the absolute value of 6i, but I'll show you a shortcut in a second. So if you want the absolute value of 6i, we want the distance from the origin. So if I think of it like this is my a and 6 is my b. So if I do square root of a squared plus b squared, I get the square root of 36, which is 6. So the formula totally works. But what I just want to show you is that for an example like this, if we think about how we plotted that 0.6i, do you remember we didn't go at all on the real axis, move left or right at all? We just went up to 6. Since that point, z sub 3 was on an axis, we don't need a formula to find that distance. We can just count. So if the complex number, when you plot it, is on an axis, you can just count to find the absolute value. You don't have to use the formula. You can use the formula if you want to, because it totally works, but you don't have to use it. All right, just remember absolute value should always be positive. So I said that was the last example, but just to show you one more, if you're finding the absolute value of like negative 3i, if we look at negative 3i, so that's 0 minus 3i, if we look at that, you don't have to write this one unless you want to. If we look at that location on the complex plane, that's 3 units away. And I know it's down 3, but don't put a negative 3, because if you're doing absolute value, you always want a positive answer because you just want the distance. You don't care about the direction at that point. You just want to know how far. And if you did want to use the formula instead for this one, it would work. So you'd have 0 squared plus negative 3 squared, and the square root of 9 is 3. But I would suggest if your complex number, if it ends up on an axis when you plot it, I would just count instead of using the formula, but the formula always works if you prefer. All right, thanks for watching. You now have a worksheet to work on with some practice problems.